Okay, hello everyone. Welcome back. So if you didn't happen to attend the first lecture for whatever reason, we do have additional printed syllabi and assignment ones in the far back corner if you want to pick those up, but they're also available online if you just want to download the PDF and do that. And of course, just as a quick reminder, we do start the sections tonight with John Seelig, who's now in the back there. And he will start those right after class in 53 Church Street. And actually, so I did say I wanted to start with light, but I wanted to mention two things because I forgot to in my slightly hurried pace earlier. And when we're talking about photos with resizing and cropping, when you resize and crop, you want to keep the aspect ratio the same. And I don't think I clearly defined aspect ratio in the first half, and that is literally just the ratio of the width to the height of the image. So, for example, old style TVs, the ones before HD TVs, had an aspect ratio of 4:3, so that the width was 4 times, or the width was 4 times some number, and then the height was 3 times some number. Usually, images from SLRs have an aspect ratio of 3:2, so they have for every 3 pixels across they have 2 pixels of height, so on and so forth. And when you do resize, you want to keep the aspect ratio the same. And usually, software tools will call this a variety of different things, such as scale, proportionately, or something else, where it will fix changing the height and the width the same amount. And this is generally what you want to do, because if you change the aspect ratio, remember from the National Geographic photo where it squeezed the pyramids, that they looked a little bit taller, they changed the aspect ratio in that. They did a resize while changing the aspect ratio. And if you are absolutely dying to hop into Photoshop, I do actually recommend something online that can get you started. And you can find it on YouTube. And it's called You Suck at Photoshop. And it is absolutely hilarious, especially the first few, and I was hoping that some of it would download over this terrible connection that I have right now, but none of it has. But it's funny and for the most part educational. If you're easily offended by foul language, then perhaps it is not the thing for you, but it is something worthwhile to procrastinate at work, for example. So, all right, moving on to light. So, when we're talking about light, we are talking about the light that we see, and this is the same light that is captured by the camera. Without this light, there's no photos. We have no way of being able to capture a photograph. And light is, I mean, if you remember from way back in your high school physics days or even college physics days, it can be defined as a photon that's moving, and it has properties of both waves and of a particle, a variety of other things, but really you can think of it as this electromagnetic wave that's moving through the atmosphere or through space, for example, that has a specific frequency. And we can only view a very narrow portion of the frequencies that are possible by electromagnetic radiation that is propagating throughout the universe. And so, but because of this sort of duality of properties, where it has both properties of waves and of particles, and you may be kicking yourself for maybe wanting to pay more attention back in your days of high school physics. Don't worry about that too much, but really what's interesting is that because of these two properties, that light behaves as a wave and also simultaneously in some ways as a particle, it impacts us as photographers in very, very real ways. And each one of these properties actually impacts us in a different way. So because of the way that it propagates as a wave, we have to deal with certain things, and because of the way that it's actually a photon, it's a particle that's moving through, or it can act as a particle that's moving through space, that also has a specific impact on us. And so if we're talking about particles, you can think of light as just being well, I mean, I already described what it is, but because these photons are moving through space, the number of photons that reach us or that reach our eye impacts the intensity, or how bright that specific light source seems to be. So the sun, for example, is giving off lots and lots and lots of photons and electromagnetic radiation. Of course, it's all throughout the spectrum, And incidentally, for those of you that don't know, I did my undergrad studies in biology, and I took as a side class, there was one class where we were talking about this a little bit more, and what was really interesting to me was that the peak of the sun's output in terms of radiation. So if you were to take a look at a graph of how much of each of these frequencies our sun is outputting, you'll actually notice that the peak is in the visible spectrum. And this is actually very interesting from an evolutionary standpoint, because we have evolved then to be more sensitive to the most efficient output from the sun, which I think is actually a pretty interesting side story. But anyway, if you're ever wondering why we see that specific part of the spectrum, that is likely why we do it. But anyway, moving back a few steps, we can only see this small part of the spectrum, and the frequency, the wavelength, defines the color of that specific light source. So the sun, it has white light because it's a mixture of all of these colors. But if you were to take a look at just like a red LED, for example, the one that you might find on the back of a camera or on your cell phone, it's really only emitting light in a specific spectrum up here. Fluorescent lights, for example, give off a certain set of spectrum, or certain set of spectra rather, and it's very heavily weighed towards the green side, although there's some spikes elsewhere. And if you were to take a look at some of these sources of light, it's actually very interesting to see how they output these wavelengths. But what is important, what is really important for us in our discussion today about light as it applies to photography is photons, and that because it also acts not only as a wave but also as a particle, the number of photons that reach us matters. So the more photons that we see, the brighter something appears to be. And in fact, we can double or have the number of photons, and that will literally double or have the brightness of a particular scene. And so while that may not appear to us to be twice as bright or half as bright, because our eyes actually play some tricks on us that I'll talk about in just a little bit, we actually, when we're using cameras, this actually impacts us in a very, very real way. So the eye. So I did mention that I did study some biology, so I have to go over some of it here. But this is really just to be, because we're going to make a comparison from our eye to cameras. And as you will see shortly, there is not actually, there's obvious differences, but there's actually some very striking similarities between how we see and how a camera takes a photograph. So light comes in through the iris, and it gets focused by the lens that's here. Just as our camera would focus light into the camera's sensor through the lens, we also have a lens in our eye that focuses light onto the back of the eye. And the really important bit, and what provides us with a lot of our perception of light, or rather the perception of detail, is this small center called the macula. And within the macula we have the fovea, and there's a whole bunch of cells in there that provide us with a lot of the detailed view that we can actually see. And so you'll notice that one of the things that's coming out of the eye is the optic nerve that's protruding out of the rear, and because of the placement, because the optic nerve connects to it's not quite the rear of the eye, but it's slightly off center depending on which eye, it's either on the left or the right. There are actually no rods or cones. There are no cells that are capable of capturing light there. So you literally have a blind spot where the optic nerve meets the back of your eye. And in fact, you've probably seen a variety of optical illusions or optical tests where you can see two dots on a screen, for example, and they say, okay, move your face to a certain distance from the screen, looking only at one dot, and then all of a sudden the other dot disappears. That's because that dot is all of a sudden right underneath, or the dot is being displayed right here, right over the optic nerve, and so your brain, or your eye rather, cannot see it. But what your brain is doing is playing a trick on you, and it's filling in the surrounding colors and the surrounding detail into that portion. So what is transparent to us, what we don't notice, we don't see a black hole sort of where that blind spot is. Our brain still perceives something that's there, some bit of data, but this can actually impact the way that we view a scene. And in fact, it's a very real, it's a very, very real problem, especially when we need to, when we are doing something that, is very heavily dependent on vision. So driving, for example, if something happens to be coming at you in that very small portion, you may not ever see it. And it's actually a very plausible description. And in fact, I've noticed, at least in my car when I'm driving, that if I'm looking right down the center of the road, sometimes the line on the right side is right under that spot, and I can't actually see the very far right part of the road because it's where the optic nerve is meeting my eye, and it's actually sort of disorienting when I notice it because I'm like, oh, where's the edge of the road? But it's still, don't worry, it's still there. You can just move your eye, just look the other way, and you will certainly see it there. So just a slightly more detailed view. So what we have here, or this is also another view of the eye. This is more top down. So we have the light that comes in through all the way up there through the pupil and the lens, and then comes down through and hits the fovea. But also, the light does scatter, and it does go to various regions within the eye here, where you have a variety of optical cells. But the fovea is really important to us for our sight, and it's a very small portion, as you can see, but this is where the majority of the cells that contain our detailed viewing, where we perceive detail, are actually present. So there are, within the middle of the fovea, there's even a smaller section that's called the foveola. And so this is getting to a bit of detail that's a bit extreme, but in there's no rod cells. We only have cone cells. So if you're familiar, there are two types of cells in our eye, rod cell and a cone cell. And the cone cell is what gives us the ability to have detailed vision. And it's only a very, very small percentage of our sight that we actually have the greatest amount of visual acuity. It's only something like 2% or something ridiculous like that, where we actually can view the most amount of details as possible. So this doesn't mean that the rod cells are actually useless. It's actually quite the opposite. The rod cells are what gives us a lot of our motion capabilities. They're what helps us see at night, but we have the greatest percentage of rod cells along the periphery. So outside of the fovea do we have a lot of the rod cells that we see. And in fact, I have here a chart that shows us the difference between some of the rods and cones and how this actually impacts us and our vision. So rods, for example, are primarily responsible for our night vision, whereas cones are responsible for our day vision. If you've ever been to a planetarium and they always tell you that when you're stargazing, one of the things that you want to do when you want to look at something at night is to not look directly at it, but look away from it, and just out of the periphery of your vision, look at something, you'll be able to see it a lot better. It is for this reason. It is that we have more rods, we have no rods in the very center of our vision, which is responsible for night vision. So we actually have no visual acuity at the darkest parts of night in the center of our eye. So you can't look directly at something. If you want to see something with more visual acuity at night, you actually need to look slightly away from it and just pay attention to the periphery of your vision. So this means that rods then are more sensitive to light, whereas cones are less sensitive to light. So the rods then are also, like I said, they're not in the fovea, whereas the cones are concentrated in the fovea, and this is what gives us a lot of the results in a lot of the things that I was just talking about. However, within the retina, within the back, the part of your eye that's responsible for sight, we do have many more rods than we do cones. So this is actually pretty important to us. But what's even more important to us, arguably, as photographers, is that rods are only, they cannot see color. They really are sort of black and white, so to speak. Whereas cones, we are able to see color through cones. And what this means is that we actually have 3 different types of cone cells in our eye. And each one can detect various types of wavelengths that we saw earlier, the combination of which our brain is able to figure out what the color of some particular aspect of the scene is. But another thing about rods and cones that I mentioned before is that rods, they're better at detecting motion. So they're a bit faster, so to speak, whereas cones are better at detecting detail. So this is why in the periphery this is why our peripheral vision is very, very good, not only at night, but also with objects that are coming towards us or away from us. We're able to detect motion a lot better in our periphery than right in the middle of our vision. So you can imagine some of the things by knowing just these relatively simple facts about rod cells and cone cells. You can imagine some of the things that might happen if we, say, lose the ability to use our rods. So what might happen in that case? Yeah, can't see at night. We can't see motion as well. And as you know, if we lost some cones, we would not only lose the ability to detect detail, but it would be difficult for us to view things during the daylight. So we'd have to wear some really thick sunglasses to block out a lot of light. But it's even possible, as I mentioned before, that we have that since we have 3 different types of cone cells, that losing one type of these cone cells can mean that we have some sort of deficiency in viewing a particular range of color. And in fact, this is where color blindness comes from, is that we lose one of these types of cone cells, and we are therefore unable to view that particular wavelength in it. And so and there's lots of different types of color blindness, and it all depends on which combination of cone cells you have actually lost, whether it is the S, the M, or the L. And so you'll notice that these are labeled such, S, M, and L, but our eye is made up primarily, where there are cone cells, is made up primarily of the M type and the L type. So we as humans, in the average person that is perceiving color will have 98% of their cones will be M and L types, and only 2% will be S types. And so what this means to us is that we actually can discern green and red a lot better than we can discern blue colors. And so, I mean, we could turn this again into some sort of an evolutionary argument where, sure, a lot of the Earth is green, and so we need to be able to detect various types of green, so on and so forth. I'm not really sure if that's exactly what's going on here, but it is what it is. And so this is very important to us, that we cannot detect, just like if you're familiar with how well we can detect audio. We can't, so low frequencies, for example, of what we can hear, it doesn't sound as loud as higher frequencies, but not the super highest frequencies, if that makes sense. So we have this sort of changing perception of sound. So to really hear low frequencies really loud, we have to really turn it up high. It's the same sort of thing with color, where blue color or short wavelengths are more difficult for us to perceive. In fact, don't appear as bright as green and red. Yes? Would that have something to do with color blindness? Does this have something to do with color blindness? What do you mean?
Well, would there be something off in the rods and cones in somebody's eyes why they can't see like certain colors?
Yes, well, color blindness arises from the fact that one or more of these cone cells are missing.
That's what I was...
Yeah, so for example, if someone loses their S cones, for example, and I forget which type of color blindness is the most prevalent, but then they will lose the ability to perceive blue color blindness. However, I expect that because we have such a high percentage of M and L type, that it's probably red-green color blindness is probably one of the more not popular, but one of the more prevalent ways of boy, open mouth, insert foot. One of the more common ways to lose the ability to view color, just because we have so much greater percentage of those in the average person. But anyway, the M and the L type, so these two, and I guess this is another reason why, these two types of cones are on the X chromosome. And so because males only have one X chromosome and a Y chromosome, it's very easy for there to be a mutation or deletion in one of those genes, then therefore one of these two cells is just not present. That's why it's much more prevalent in men than in women. But anyway, this is important to us, but also it's really useful to know that green and red are much more important to our vision than blue. And this will come in handy in a few lectures when we're talking about digital cameras. Even digital cameras use this fact to try to help them when they're taking a photo. And how we detect brightness is greatly perceived by how many of these cone cells we have. So because we have so many of these M-type cells, we can actually perceive, we use a lot of the green color information to help us detect brightness in a particular scene.